curves, we can actually sketch the curves to show how many points of intersection that we have. And the points of intersection, as you remember, are the solutions to solving simultaneous equations. So we've seen earlier, for instance, when we are solving simultaneous equations, for instance, how we can sketch it, which is and look for the intersection, and sketching and looking for the intersection gives us the solution. So suppose I had a line here, which is y is equal to 2x plus 3. And suppose I had a second line here, which we can call it as y is equal to minus x. The point where they intersect is the solution to these two equations. If we were to solve these two simultaneously, then we would say that where they meet, both the y values and the x values are the same, so we can substitute one y into the other, so you get minus x of one equation equaling to 2x plus 3. And so what we should understand here is that the left-hand side of this equation comes from here, y equals minus x, and the right-hand side of this equation, 2x plus 3, comes from here, y equals 2x plus 3. So this is interesting because this gets us to think about equations that we see differently. So whenever we see an equation, we can think about the left-hand side being represented by a curve. And we can think about the right-hand side of the equal being represented by another curve. And where these two curves intersect, that's where that's the resulting solution of that equation. So if we were to go and solve this equation algebraically, we would add x to both sides, resulting in 0 is equal to 3x plus 3. Then with minus 3, so you'd have minus 3 is equal to 3x, and x is equal to minus 1. And when x is equal to minus 1, we can go and find out what y is by substituting into another equation. That gives us 1. So we can see the solution here is minus 1, 1. And that's the solution coordinate of that point that we have here. And we solve that algebraically, and that fits with the graph as well. We can see that's where they intersect. So really, going back to basic linear equations that we've been solving, the left-hand side could represent a curve, y equals something. So this be y equals minus x, and this be y equals to 2x plus 3. So all equations, when you're solving, you can actually think about the left-hand side representing a curve and the right-hand side representing a curve, and so you can visualize them in that manner. So let's take a look at how we apply that to this particular example. So it says here on the same diagram, sketch the curves with the equation y equals x minus 3. So we've got our axes. Y equals x minus 3. You can see this is a quadratic. X times x positive, coefficient to x squared. So it will finish up here somewhere. What are the solutions? I can see they are x equals to 0 and x is equal to 3. X equals to 0 and x is equal to 3. No repeated solutions. So it will simply go through them. And quadratic, so it will be one turn. I can go ahead and sketch this quite easily. Here's my quadratic. Okay, and a quadratic is always symmetrical. Line of symmetry going through this turning point here. Very important to recognize that. So when you sketch, make sure you have that symmetry in your sketching. So we've drawn that. Let's go and draw the second curve, which is a cubic. Let's consider everything about this. So I'm going to just write down a few things about this. Consider the 6 points for our graph sketching. So it's already factorized, brilliant. So where does it cross the y-axis first? It crosses the y-axis when x is equal to 0. So when x is equal to 0, we've got 0 squared, 1 minus 0, and that gives us 0. So when x is equal to 0, y is equal to 0. Where does it cross the x-axis? Well, it crosses the x-axis when y is equal to 0. So you've got 0 is equal to x squared, which is repeated twice. So I'm going to rewrite it as follows. And so then this gives us x equals to 0, x equals to 0, and x equals to 1. Since x equals to 0 is repeated twice, it means it will bounce off at that point. X equals 1, so it will then go through it. If we were to multiply x by minus x, it would give us a negative coefficient for the x cubed, therefore it finishes down. So as x approaches infinity, y approaches negative infinity. It's a polynomial of order 3, so it should have 2 turns. So it finishes down here somewhere. So what will it look like? Well, it will, we said it goes through 0, 0, and 1. So it will go through 1, which is here. I'll just put that in. And it will go through 0, so it bounces off at 0. So it goes through 1, comes back down and bounces off this, and then goes up again. Now what we need to understand here, as it goes back up this way, will it go through like that, through it, intersecting again with the quadratic, or will it go like that, meaning that it doesn't intersect with that? That's really important part of sketching. So since this is a cubic that we're sketching, a cubic is a higher order than the quadratic. Its steepness on this side will be steeper. So instead, what I've got here is it shows that the cubic is actually less steep than the quadratic, which is not correct. The cubic should be more steep, meaning that there will be another point of intersection here. So it's really important to sketch that gradient part or that end part of the curve by considering which one is higher order. The polynomial with the higher order will be steeper at the end. And so there we can see that there's one intersection there, there's a second intersection here, and there's a third intersection here. So this, if we were to solve these two equations simultaneously, we would have 3 solutions. Graphically, we can see those 3 intersections here. It then goes on to say find the coordinates of the point of intersection. So this requires us to find these coordinates. Obviously, graphically, we can see there are 3, but we can't find out what they are exactly. If we were to draw it to scale, perhaps we could have found out an estimate to those solutions. But we're going to look at part B here, and we're going to look at how we then go and find the intersections. So as we said, intersections is where those curves meet each other, and where they meet each other we can say that the y values are equal to each other, so we can substitute one y into the other equation. So we have x minus 3 is equaling to y should then equal to x squared 1 minus x, which is equal to y of the second equation. So here, as we said before, the left hand side represents one curve and the right hand side represents a second curve, and when we solve equations we are looking at where those left-hand side and the right-hand side curve actually intersect each other. So let's go and take a look at how we then go ahead and solve this. So left-hand side, right-hand side curves intersect. How do we solve this? Well, as you can see here, we've got an equation all involving one unknown. So let's go ahead and tidy this up first. So we'll tidy this up. We've got x squared minus 3x is equaling to x squared minus x cubed. Let's get all the terms onto one side and equate it to 0, which will result in us having x cubed minus x squared from both sides. That gives us 0 minus 3x equaling to 0. So now that we've got that, we can go ahead and factorize this, which is the best form to have any equation in x squared minus 3 equaling to 0. From here we can go ahead and find our solutions. X is equal to 0 or x squared minus 3 equals to 0, which gives us x squared equals to 3, so x is equal to plus or minus square root of 3. So we haven't found our solutions, we've only found the x values of our solutions, i.e. the points of intersection. We need to go ahead and find our y values. So let's go and determine what's happening for the other ones as well. So we've got at x equals to 0, what is our y value? Well, let's go ahead and substitute it into one of the equation. We'll use y equals x minus 3. Y equals x minus 3. Substitute 0 in there, so y is equal to 0, 0 minus 3, so that gives us coordinate 0, 0. We'll go and substitute positive root 3 in there as well. Y is equal to root 3 brackets root 3 minus 3. Okay, and that gives us 3 minus 3 root 3. So when x is equal to root 3, y is equal to 3 minus 3 root 3. And when x is equal to minus root 3, y is equal to minus root 3 bracket minus root 3 minus 3, and that gives us 3 plus 3 root 3. Okay, so the coordinate here is minus root 3, 3 plus 3 root 3. Okay, so minus root 3, 3 plus root 3 would obviously be this one here. This intersection. This intersection is obviously root 3 and then 3 minus 3 root 3. And this here, I've drawn it a bit so that quadratic should actually be passing through there. So the point of intersection there, 0, 0, is our third intersection. So we found the points of intersection there as required.